I'm actually really excited to be here with you tonight, not only because of my love for Vail and the Vail Symposium, but in part because we're really at a very pivotal time in history, not just for the Woods Hole Oceanographic and ocean sciences more generally, but really in how we can meet the moment as a society, as scientists, to address some of the challenges ahead. Lori, on the drive over from the airport, asked me, will we be talking about some of the applied uses of the science that you do? And indeed, we will be tonight. The title here is really meant to link into this, which is not only just illuminating the abyss, that is identifying, really casting a light on the dark unknown of the ocean that's around us, but really an invitation for us to unlock something we're calling ocean intelligence to address this age of global disruption. And I wanted to start with a parable. Some of you may know David Foster Wallace, an author who about 20 years ago gave his now famous commencement speech at Kenyon College. And he opened his comments with the following. He said, the two young fish are swimming along in the ocean when they encounter an older, larger fish. And the older, larger fish calls out and says, "Morning, boys, how's the water?" And they're swimming along. And then the older fish departs, and the two younger fish look at each other and say, "What the hell is water?" And the relevance of this for today and for the next 45 minutes really is it's a reminder of how easy it is for us to overlook the forces that shape our world, the things that are really, in fact, most important to not only ourselves, but our communities, to all of global society, indeed all of humanity. And it's the case I'm going to make for the ocean tonight is that's the number one hero of the story. Now, I don't think Wallace meant us to take this parable as literally as I'm about to, but the fact is we're all alive today. We're all experiencing the well-being that we have because of the ocean. And that's something that's lost on us, and especially when one lives in the middle of a continent, it's really easy to overlook the ocean. Although I did a short little head count, and actually a lot of you have houses on the water. So I think many of you have personal connection to the ocean. But most of all, you have my sincere gratitude for being here tonight, not only to hear me, to hear about the ocean, the Woods Hole Oceanographic, but really what we can do as a society to really muster the courage and the commitment to answer that question. So I would ask all of you to sort of close your eyes for a moment and sort of envision what you think of as the ocean from a planetary scale. And if we're asked to draw a picture of the map or a picture of the world from memory, we'd probably come up with something like this. You'd see a Mercator projection, you'd see North America and South America lined up like that. You'd see all the ocean basins that you had to memorize as a child, and you would sort of get a sense that, yeah, that makes sense. That's the world that we know. And I'm here to tell you, no, it isn't. I'm going to do something that's going to blow your mind. Probably many of you haven't seen it. Now, one can look at the Earth from many different projections. You can look at it Mercator, you can look at it elliptical, you can look at all these different. What I'm going to do now is split the seams of the globe baseball, if you will, along the lines of the Bering Strait and down the axis of the Andes of the mountain chain runs down North and South America. You with me? So what we're going to see is how the ocean looks to something living in the ocean. And this is the first time we're showing this to any audience. It was developed. We're going to show it to you again so you can sort of get a sense of it. This is the map you know and love, and you know where you are. Now I challenge you to say, where am I? Right? But to a fish, to a whale, to a plankton, they know exactly where they are. There's one ocean. We are an ocean planet. It's 70% of the area of the planet. If you look at us from space, what color are we? Blue. So from the perspective of plankton or ocean or a fish, this is what they see is there's one ocean. It's not just one ocean, But now what I'm going to do is animate this with the ocean currents. And what you're going to see is that it's one interconnected ocean. The yellow lines are the tropical currents. That's actually the equator is running north-south in this image, and then it bends around across Africa. If you can see Africa there, you can see that the projection is centered on Antarctica, and then you can see the continent of Africa, you can see North America. Opposite of Africa is Brazil, and you can see that there's this flowing of currents that connects all the ocean basins, and it takes about 5 or 10 years for the water to make that course. It's this big, moving, interconnected fluid that we see as the ocean. But this is just the surface of the ocean. The ocean has an average depth of about 4,000 meters. It's not just one vast, interconnected ocean. It's also one vast, interconnected, and living and breathing ocean. This is an animation of chlorophyll, both on land and in the ocean, across the seasons. And you're going to see it move up and down throughout the seasons for many years. Whenever it turns green, it means there's a lot of algae in the water. Whenever it turns blue, it means it's more like an ocean desert, like the water off of Bermuda, for example, or off of Florida. And so you can see that the Earth is actually breathing. This is the uptake of carbon from the atmosphere during Northern Hemisphere spring and summer, and then the release of that carbon during fall and winter when the plants go into senescence in the wintertime. It's driven largely by the Northern Hemisphere because there's more Northern Hemisphere land than in the Southern Hemisphere. But the planet is definitely breathing. In fact, if you take a breath, one more, that second one comes from the ocean. Every other breath you breathe is coming from these little algae and plankton in the ocean. You don't see it, you don't know it, but every other breath is a reminder that the ocean is your friend. Now, we'll return back to this projection. It's called the Spillhouse projection, who was actually a scientist at the Woods Hole Oceanographic from the late 30s until the 60s. And he came up with this projection with this idea explicitly in mind to express the idea that there's a single ocean. It actually went viral on the internet when it was actually first developed into a map by a company called Esri, and it just really sort of took over the world. But I'm going to introduce a paradox, and here it is. So we live on a planet, it's an ocean planet, it's mostly ocean, and it controls everything we care about. It's a case I'll make in a moment, but food, water, shelter, energy, coastline, national security. Economically, 90% of goods travel on the ocean. Medically, most of our medical advances have come from molecules discovered in ocean organisms because of the diversity of life that exists in the ocean. Nutritionally, we get 20% of our protein from the ocean. And militarily, we are a maritime nation. And our military strength rests on our naval understanding of battle space awareness, which is a cornerstone of our national security. But if you were to ask an oceanographer, you ask me, and I will tell you the first truth, which is that we know next to nothing about the ocean. Just to kind of drive that point forward, I did a little math ahead of this meeting, and I guessed the shape of this room, the dimensions just about right. So it has seats for about 200. I'm told you have to really pack them in if you bring them in. So we've only explored, or only mapped about 25% of this area that you see here of the ocean. We've only taken a ship and it's beamed the seafloor about 25%. The rest of it is kind of a guess. We've only been to about 0.01% of places on the seafloor. So if you look at the square footage of this room, all of human endeavor in the ocean, I did this, all the places we visited are that big relative to the size of this room. Everything I'm going to talk to you about, everything you're going to see from me, which is just what I can say in another half an hour, was a piece of this piece of paper. And there's all of this to discover. Imagine if that piece of paper were on this chair. I would think the entire deep sea floor was a chair. If I put it on one of you, I'd say it was one of just like you as a person. I would fail to miss all of the elegance of a space like this. So this is an invitation for us to think differently about how we're approaching our exploration of the seas and our knowledge of it. Now, all of you are familiar with AI, whether you are a leading scientist in it, or whether you use it, or whether you've read about it, or you've seen some really funny TikTok videos about it. But I invite you to imagine what we could unlock if we trained our understanding of the ocean. Somebody didn't turn off their phone. James did that. But imagine if we could develop our same level of understanding of the ocean as we enjoy at our fingertips with the evolution of AI just in our recent lifetimes. So artificial intelligence today is the training on these vast structured data sets that are scraped from the web, that represent the web presence of human knowledge and experience. And that's what it's spitting back at us, is what it has learned, what it has developed knowledge about, what it's trained on, and then provides solutions to specific queries that are brought to us. What we're missing for the ocean is the corollary of that, which is ocean intelligence, which I would call our ability to truly know the ocean at the space scales, both in the time scales that the ocean actually operates, to basically replace our ignorance about the ocean with tremendous and deep knowledge. It's a way for us to really think about the ocean in a different way. And if really my presentation is about anything, it's really to get us to think about the ocean in a different way, from that mind's eye of it's a big, blue, vast place that many of us haven't been to this thing that's fully responsible for our lives and livelihoods. Now, deep sea exploration, and exploration just in the ocean generally, is really a very different kind of science, and it really requires a very different kind of scientist who does it. We spend weeks, if not months, at sea. I've spent many years of my life at sea. I have colleagues who have been on 90 or 100 what we call cruises, but they're really expeditions when you're at sea in conditions like this. It takes grit, it takes persistence, it takes ingenuity, it takes flexibility. And what we're really trying to do is really to press the limits of our knowledge, to dive deeper into how we can learn more about the ocean. The ocean doesn't yield its secrets very easily. In fact, it does everything it can to thwart our best efforts. But the rewards are beyond extraordinary. So what I'm going to do is just give you a snapshot about what some of that looks like. But this is the kind of conditions that we do our science in. Now, when many of you think of ocean life, you might have this beautiful image of this charismatic megafauna here, this beautiful whale taken by one of our scientists. It's just this, the gaze in that eye is really something. And this is an incredibly high resolution photograph that was taken by one of our people, Richard Beavers. And the ocean is not just awe-inspiring, but it's also just incredibly beautiful. But I'm not going to talk about this guy anymore. Most of the life in the ocean, everything that you saw from that satellite image of the chlorophyll, is life that's very small. These are phytoplankton. These are microscopic algae that are photosynthesizing, just like trees and plants and grass on land. These photosynthetic algae are responsible for that greening up of the ocean that you saw in that breathing slide that I showed earlier. And if you were to zoom in and grab a scoop of this water, and typically the way that we would do an analysis to get these images shown here on the right would be a scientist would go over to the rail of the ship, drop a bucket in the water, bring it back up, grab a pipette of that water, put it on a slide, look under a microscope on a moving ship, I remind you, and then look at these things as they're sloshing back and forth. Nothing will make you more seasick than looking under a microscope at sea. It's incredibly terrible work. The people who do it love it. I just can't endure it. And there are other biologists that also felt that they couldn't endure it because it's not just those beautiful little diatoms that you see, and they're shown here in this sort of more black and white image. But if you zoom in, the diversity of life that you see, not only in shapes and sizes, but as you get to the very, very, very small, to the picoplankton, like this guy, Synechococcus, that's only 1/10 of a micron in diameter. There's 1,000 of them to the width of a human hair. This guy alone is responsible for 1/2 of that breath that you got from the ocean. It's called Synechococcus, and it's the most widespread cyanobacteria on Earth. And it's this humble little, beyond microscopic. You could not see it on a microscope. You have to look at it with a transmission electron microscope to be able to see it. Now, it's another thing to kind of blow your mind that, okay, it's very small. Okay, it's really abundant in the ocean. Still, it doesn't really move me. Well, the combined mass of this guy and all the other photosynthesizing plankton in the ocean is 1.5 billion whales. These things are so abundant in the ocean that they just dominate the life system. And we don't see it, we don't know it, but we take that breath, and that's how we know that they're doing their job. So one of our scientists, Heidi Sosik, said, I'm pretty much done with looking at plankton at sea and trying to identify them. She said, I think we can do better. We can build a robot to do that. And she developed with her engineering friends at the Woods Hole Oceanographic an imaging flow cytobot. It's kind of a catchy name. IFCB is not quite so catchy, but what it does is nothing short of phenomenal. It will take a sipping stream from the water intake of any hose that's put overside or on a ship. It'll sip that seawater in, then it runs it through a very narrow capillary, a glass capillary, a channel, so that it can count individual phytoplankton. You with me on that? And then it has a laser that says, are you photosynthetic? Because if it fluoresces, it's got chlorophyll in it. And then it says, if it fluoresces, I'm going to take a picture of you. So it has a very fast frame rate camera, and it takes these pictures by the billions. Every second of every hour of every day of every week of every month that this ship is crisscrossing the oceans. And it basically makes a Facebook every half hour or so of who's there, what's the ecosystem, counting millions of these things and saying it's all these kinds of people, or it's all those kind of people, or it's this mix of people. It's doing that all the time and soon everywhere. So just last year at the Woods Hole Oceanographic, I funded Heidi. We have a new way of really accelerating cutting-edge science by investing in our people with a much greater investment in them. And so she put this robot onto a ship that every 2 weeks makes a trip from New York to Bermuda and back, delivering containers, delivering goods and fuel and the like to Bermuda and going back and forth. Well, we turned it into a measurement lab. And so what you're seeing here in blue and yellow is the abundance of something called a dinoflagellate. Anybody heard of harmful algal blooms? So dinoflagellate is one kind of an organism that has harmful algal blooms. It looks like that little guy over on the right. So this zigzag is the concentration of just this one particular kind of phytoplankton in the ocean across this transect. Now imagine if we could do this everywhere in the ocean for all the ships that are crisscrossing the ocean. We could have a real-time, AI-informed snapshot of the whole ocean health ecosystem on an hourly basis. This capability was just proven about 6 months ago. Now, to really have a wow moment, just last year, NASA launched a satellite called PACE. And PACE takes very, very high resolution images of the Earth everywhere, but it's especially tuned to pick up small nuances in color difference around the world. And the reason why is that, remember that, that really tiny phytoplankton that I showed you earlier, Synechococcus? If you had a bottle of Synechococcus, it wouldn't be green, it would be pink, bright pink. And then another kind is green, another kind is blue, another kind is yellow. And so the ocean actually becomes tinged with red or yellow or blue or green or purple. In this case, this particular one actually is kind of purple looking. This is artificial color, or this is, a computer rendered color. This is some of the very first images obtained from this satellite that was launched on Elon Musk's launch system, SpaceX system. This is actually that satellite being deployed. Once it got stabilized, it started collecting data. We got some of the very first data, and using the color, you can say that this whole purple area is Synechococcus, and the whole green area is something called pico-eukaryotes. But the idea being that, look at that resolution. The problem is we can't calibrate it. You can't say, oh, it's this concentration of Synechococcus. But now we can, because we have this in situ real-time data as we crisscross that line between Bermuda and New York. And so we have some of the very first data to calibrate this satellite and say, this is how many and how much of all these different kinds of plankton. And this is the core of every other breath of oxygen you take. And this is the very first time, literally in the last 6 months, that we've been able to develop this kind of global awareness of ocean health. So the whole ocean health, ocean productivity storyline underpins a much bigger idea, and that is something called the biologic pump. The ocean is nothing if not this moving, flowing, turbulent fluid that is packed with life. We all know that because we get seafood, we know that because we see algae, we see seaweed, we see lots of things. But that activity of life is restricted to what's called the euphotic zone, the sunlit waters of the surface of the ocean. It's not the whole volume of the ocean. So that sunlit portion of the ocean is taking up carbon from the ocean, fixing it or turning it into life, bodies, cells of organisms. That's the basis of photosynthesis in the ocean. And then that stuff dies and sinks, gets eaten up the food chain in the ocean, and it dies and sinks, and it is excreted. And it falls through the ocean like this marine snow. You with me on that kind of image? And it goes down through the bottom. Well, the ocean is 4,000 meters deep, and it's the terminal recipient of all this waste that's coming down from the photosynthesis of the ocean. So there's a pump that takes carbon from the surface ocean and pumps it to the deep ocean. Now, because it's taking it from the surface ocean, it gets replenished from carbon from the atmosphere. And that carbon is actually, the ocean's responsible for taking up about a quarter of all of our carbon emissions every year without fail. Without the ocean, this would be an uninhabitable planet right now because of our own activities. Now we're going to go deep. We're going to go on a dive. We're going to leave these sunlit portions, the beautiful whales, the great little phytoplankton, and we're going to go deep. One of the challenges of going deep is not only that it's really deep, it's really cold, it's absolute dark, black, it's corrosive because it's salty. Everything there wants to kill you. Just to give you an idea, this is the pure titanium hull of one of our autonomous vehicles called Remus. And it's only about a little less than a half an inch thick of solid titanium, the hull. And this is one of the hulls that failed during one of our routine deployments. These are about $1 million each, these robots. And you can see I'm kind of hefting it. It's heavier than it looks. It's probably, I suppose, lighter. Titanium's pretty light. But those those edges where you see that's been punched in by the pressure, that was at 2,000 meters water depth. And it just crunched it like a toy. Now, This is our deep submersible Alvin. The human-occupied Alvin contains 3 individuals, a pilot and 2 observers or scientists. One of them's looking out the window. You can see him or her looking back at you. This is at about 4,000 meters in the ocean. The hatch, so the part that the humans occupy in this is a big titanium sphere that's 4 inches thick. So instead of being a ½ inch, it's 4 inches thick, solid titanium. And the hatch that you get into is 19 inches wide. You get in and it's pretty tight. For people who are claustrophobic, you wouldn't like it. But when you go down there, it's very, you don't hear anything. There's no creaking or buzzing or anything. You just go down and it's silent. But what you notice is that the walls of the sphere get cold, get very cold. They actually get below the point of freezing, because actually the water off of Antarctica has an average temperature of about -2 degrees centigrade below freezing. It's because it's salty. One of the things you notice is pretty disconcerting, is suddenly you're looking out your porthole, like this guy is, and you notice water weeping in around the window. And then it starts to gather, and gathers a little bit more. And I go to the pilot and say, what's going on here? Should we be concerned? He goes, no, just get a Kleenex and dab it. You taste it, the water's fresh. It's the condensation of your breath because it's so cold. So I'm going to take you on a dive that I did about a couple of years ago. This is our research vessel, Atlantis. We have 2 global class ships. This is the sail of Alvin, where you go into the hull. Going down, that's me being lowered over the side, going down in the ocean. And now we're going to dive. You start in the ocean and you look around, you see nothing but bubbles. And you're in this beautiful aqua of ocean that you probably have seen. And then you go through this emerald that you've never seen with a saturation and depth. And then you go to this incredible, just rich indigo that's just impossibly deep. It's colors that you never see as a terrestrial being. And then finally, it goes to absolute black. And then what you notice is, going by the windows, are all these lights, stars falling upward. And it's all the bioluminescent organisms that are in the deep part of the ocean. These bioluminescent organisms, when you get down to what's called the twilight zone, the place where light goes to extinction, the deeper parts of the ocean, everything communicates by light. Light is the lingua franca of the majority of the ocean. Everything flashes and blinks and oscillates and vibrates, and it's just a fireworks display down there. In fact, you can send out a deliberate pulse of light, and it'll all talk back to you. It's an amazing experience, and just this is coming from a geologist. It's just amazing what you see down there. And the other aspect that's hard to relate on a screen like this is the 3-dimensionality of it. So you're looking into a depth, a volume that's alive and moving. It's just really something else. What's, again, even more awe-inspiring is that this thing that we've just dived through, going from the sunlit portions of the ocean down through the twilight zone, this is the largest animal migration on the planet by far. This is a place where all of ocean life in the twilight zone goes down to the bottom of around 1,000 meters, 3,000 feet during the daytime, because it wants to escape the predation of the sunlit surface waters. And then at nighttime, it goes up. And then it goes back down again. So twice a day, in every part of the ocean, in every sea, this is happening, and none of you have seen it. It's not only the largest animal migration on the planet, but it is also this action, if you will, of the carbon pump that we talked about for the ocean. So this twilight zone migrates up and down the ocean. And then if you ask, well, who's there? Who's doing the work? And it's these guys. They're called bristlemouth fish. And there's dozens upon dozens of different species. They're about the size of your finger or a little bit bigger. You see all the light organs along the side. And this is the most abundant vertebrate on the planet. There's about 3.5 chickens for every human. There's about 100,000 of these guys for every human. There's about 1 per square cubic yard or meter in the ocean. They're just so abundant. Bristlemouth. So one of the questions is like, well, who's down there? What are they doing? How do we know? Because remember, all we have is this. We have no idea about these guys who are living down there. In fact, they make a habit of making sure we don't see them, because the minute you get a net down there to scoop them up, they just flash away saying, danger, net coming. And you can see, we have imaged them scattering away from the net. So you'll often come up with an empty net. So we developed an acoustic method to image the twilight zone. And some of you may be familiar with a fish finder on a boat. It's basically something you put on your hull of your boat, sends out a ping, and the ping comes back if there's a fish below, because it rings off of their swim bladders. So this is a very expensive, fancy fish finder that we developed at the Oceanographic. And it does something really cool. Rather than having it at the surface, we take it down to 600 meters, about 1,800 feet in the ocean, where it's 1,000,000 times quieter. It's nearly absolute silent down there. And then instead of pointing it down, we point it up. And so it's like doing an echogram on the organs of a body. When you want to image the inside of your body, you can use these acoustic methods to interrogate the volume. That's what this does, but in a really amazing way. So these are data that were just collected. This is built for an experiment that we conducted at the Oceanographic. And it's about 100 kilometers south of Martha's Vineyard. And I just want to pause for a moment to acknowledge the technology that was developed for this. So it says anchor there. It's a big sort of 6,000-pound weight that sits on the seafloor. But then it's connected to an acoustic release, which is basically releases when we send a code to it from the ship saying release. But then this whole line, this mooring, is not just a piece of rope or something. It's this very complicated, special built conducting coaxial cable that provides power and high-speed data and connections to satellites to download data. I mean, it's just an incredibly huge technological achievement. So for the first time about 1.5 years ago, we got the data back on this image. So what we're looking at is just like you're looking at with a sonogram on your stomach or something. The bottom of the image is about 600 meters, and the top of the image is the surface. You with me? So this is surface at the top, 600 meters on the bottom, and then what goes along on left to right is time. And you can see where it says day, that's the local day, and where it says night is the local night. Remember, this is just stationary. And so you can see what the twilight zone diel migration looks like in real life. What's red are these fish and anything that reflects sound. And basically, I did a little calculation that zoom during the daytime into night of it going up into the nighttime surface ocean. That zoom, for the size of the organisms that are doing it, is equivalent to a human running a marathon. It makes its way up and makes its way down with about that same proportional speed. And you can see it just goes up and down and up and down. What this image fails to show you is that it's not just a bunch of red blotches and a bunch of blue blotches, but if I zoom in to anywhere on this image and say, give me, what does it really look like? Well, sorry, that's this is the undulation of the twilight zone that I just showed you there. But when we zoom in to one of those reddish areas and say, well, how many fish are there? Our fish finder is so precise that we can image every fish in the water column from 600 meters up to the surface. Every little smiley face there is a fish. And not only that, is we can actually watch them move. And what we discovered is they don't just like swim up and swim down. They all swim in a helix, going up and down. Again, just discovered about 1 year ago. It's just phenomenal. We don't know why. So one of the other cool things that we did as part of this project, some of you may know the TED Audacious program, a TED Audacious Fund. We were a recipient of a TED Audacious Award. In fact, the first recipient of a TED Audacious Award just concluded a couple of years ago, but it was roughly $34 million provided by philanthropy to discover the twilight zone, ask these fundamental questions about the twilight zone. And so one of the portions of that experiment, of that project, was to tag apex predators like this shark, this blue shark. He was tagged just off of Woods Hole. And I'm going to go back to this because I'm speaking too slowly. One moment. Okay, watch. He was tagged off of Cape Cod, and he goes out eastward, but then he hangs out by that red spot and just starts hanging out. Well, that red spot is an eddy, a city-sized storm in the ocean, these big kind of swirling gyral motions that are in the ocean. Well, it turns out these are places where life in the ocean gets concentrated. And so he's basically going to the sushi bar. He's able to go there and just feed along the periphery, and we can actually watch him dive and go up and down along the wall of this gyre. It's just, again, behavior that hadn't been detected before. So sharks do this, tuna do this, swordfish do this. For those of you who've eaten swordfish, about 90% of the tissue of the muscle of a swordfish is actually fed by those deep sea Twilight Zone fishes that I showed you earlier. So I can sort of tell you that, and you can say, yeah, or you can be curious yourself and say, well, let's cut them open. So we cut this particular swordfish open. Inside, we found a fish, and the name of the fish is called a lancet fish. And you can see at the top, you see the teeth and the eyes. Can you see that? What else do you see? There's another fish inside the fish. It's like a Russian doll. One pointing downward. See the eye and the tooth down below? So inside the lancet fish is a barracuda. Inside the barracuda are, drumroll, lanternfish. These fish that I showed you earlier. Here we had 4 trophic levels in one organism, in 4 trophic levels of fish, which are all top of the food chain. So it just gives you an idea of the complexity of the food webs in this place that none of us have ever been to, probably none of us will ever go to. And yet it's, again, essential for the planet. Now I was going to ask a question. How many of you have been on a safari? Oh, this is great. Yeah, okay. So when you go on safari, you travel by Jeep, Land Rover, and you drive around, but when you really get to something great, what do? You park under an acacia tree and sit. Don't make a noise, right? That's your way of observing. We couldn't do that in the Twilight Zone because we didn't have a way to sit there and sit quietly, right? We didn't have a robot that could just sit there, so we built one called Mesobot, for mesopelagic robot, Mesobot. Mesobot got a fresh coat of paint, looks really cool. This is an undergraduate student. Actually, no, this is a high school student named Charles Essex. Charles said, I got an idea. What if we built a lure? So instead of just going down there waiting for something to happen, what if we go there and make something happen and try to attract something? So he built this sort of tennis ball shaped thing that's covered with LED lights that you can flash and make it look like a squid or make it look like a shark or make it look like a jellyfish or whatever you want to do. Like you saw the colors in the previous image. Well, you can train it and say, okay, you're gonna look like one of those things. So he did that. And if you show, this is just it doing one thing. You can see all the little LED panels on there. It's about that big around. And it hangs off the front of Mesobot. Mesobot has 2 high-definition cameras in the front, and it can autonomously, meaning you literally throw this thing over the side, it goes down to 2,000 meters, and sits like a Jeep under an acacia tree. The very first time we deployed this was, I think, about 1.5 years ago, maybe 2 years ago now. I'm going to show you the sort of raw footage. It's the first thing we see. This shark goes by, he's like, what is that? But he goes by, and then he comes by again, and he's like, I want to see if you're edible. And so here's the dash cam. And he shows he uses his dorsal fin to kind of nudge it and get a response from it. And then he's like, that thing didn't feel good or look right, didn't taste good. And then he comes back and investigates. So this is all using red light, which they can't see, but we can see them. And just imagine what we can learn if we do more than this piece of paper. So all of that I've shown you is part and parcel of this carbon pump whereby the ocean takes up carbon from the surface of the ocean with photosynthesis. It sends it down deep through the twilight zone and eventually makes its way into the deepest reaches of the ocean. When you get down to 2 or 3 or 4,000 meters in the ocean, the carbon there, if you could radiocarbon date it, it's hundreds to thousands of years old. And the reason is that the deep parts of the ocean are ventilated very slowly. Unlike the surface where you've got lots of waves and currents, the deep ocean moves and circulates very, very slowly. Consequently, it's a big piggy bank for carbon. It's the largest reservoir of carbon on the planet. It's 50 times more carbon in the ocean than is in the atmosphere. 50. It's this elephant of carbon storage on the planet relative to the atmosphere. Just to give you an idea of how big it is, if you could capture all of the excess carbon that's in the atmosphere because of human activities, the whole climate change problem, the whole thing, if you could get it all together from the atmosphere, put it into a ball, put it into the ocean and mix it like a martini in all the ocean basins, top to bottom, it's a 1% addition to the ocean carbon's content. The ocean is that vast. And you can say, oh, we can never do that. Well, it happens all the time. It happened during the last ice age, happened in the ice age before that. The ocean stores carbon down deep, and then it burps it back out again. It does this naturally. So if we continue to the seafloor, to one of the places that's represented by this piece of paper, this is a video clip that we put together of Alvin on a dive to some new hydrothermal vents with our new hardware, our new cameras, our new lighting systems to bring you sort of a telepresence of what it's like to be there. You've probably heard and seen these tube worms before. We led the discovery of these tube worms, and they are a completely new modality of life. If you were to look for life on another planet, you'd look for these guys because they make a living not from photosynthesis. They don't require any photosynthesis. They rely on chemosynthesis. They pull chemicals out of the water to sustain this whole diversity of life that you see. Everything here is fed by dissolved rock that comes from these deep sea vents. And so when we're down here, again, you discover this world that, again, none of us will probably visit, but just represents this tiny little portion of what we can see. These black smokers, when we first measured the temperature of them, they can get up to 600 degrees centigrade. When we first measured them, they melted the probe. They went with Alvin to put a probe in it, and it melted. And so he's like, we got to back away. But this just gives you an idea of what it looks like when you bring intentional presence to the deep sea to really imagine what it's like to just visit this one piece of real estate in the deep ocean. And as you continue through the deep ocean, as we do, you explore other things and discover other things. And one of the things that we'll discover are the lowly sponge. So the deepest parts of the ocean, the broadest expanse of empty ocean are in the Pacific Ocean at great depth. It's there where we find these manganese nodules that you may have heard about. And on top of many of those manganese nodules, you'll see this kind of a thing, groups of sea sponges growing on top of them. Now, when we radiocarbon date these sea sponges, they are 10 to 15,000 years old. They're the oldest living creature on the planet that are still alive. And they are still alive because they've made their life of filtering. I don't know if you know how they work, but this beautiful helical structure they have will actually take deep sea currents moving horizontally and turn it into a convection tower. So that it actually filters because of the sideways flows. It filters vertically where the sideways flow. So the sponge's job is basically to extract this meager, very slow life out of meager resources in the deep ocean. But as a result of having to basically not catch a cold ever in 15,000 years, it has these incredible defense mechanisms. In other words, when you take one of these from the deep sea and bring it up to the surface, it's not like, oh, that's a sponge. It's like, whoa, get that thing out of here. It stinks. It smells like pine sol. It has this incredible smell of deep organic chemistry to it that's just like benzene almost. It's this really strong smell. And it turns out that deep sea sponges are loaded with these molecules that have incredible like a vaccine quality to protect it from deep sea viruses. And so the antiviral compounds here served as the base molecules. We wouldn't have known about this molecular structure were it not for these guys. Well, we'll go to the bottom, Retrovir. Probably everyone in this room has heard of that. That's the popular HIV/AIDS drug that's used. For anyone who's had breast cancer, there's Halaven. Hopefully nobody here knows what this is, but that's one of the common treatments for breast cancer. Leukemia and lymphoma is another base molecule, all captured from a small portion of the seafloor that we explore. So now we're going to sort of come up to the surface of the ocean from being down deep. We could stay down there a long time. This is what it's like coming out. It's really exhilarating when they actually get yanked out of the water. It's pretty amazing. It's just like, sort of like coming back from space, but different. And now we're going to sort of look at how we're developing this kind of larger sense of the ocean, sort of an internet of sensors that we're part of. And these are robots. There are about 4,000 robots in the ocean that have a very simple job. They're about as smart as your toaster. And they basically do one job. They stay at the surface, and they sink to 2,000 meters, and they come back up again. And they phone home, download their data, and go back down again. They'll do this for about 4 or 5 years before they run out of juice. This is actually a snapshot of what they looked like a little over, a couple of years ago. And the way this works is as follows. Let me see if I can show this. This is what it looks like. It's a yellow, it's about as tall as I am. The instrument panel's on top. And basically, we launch it in the ocean with ships of opportunity. It can be any kind of a ship, sailboat or whatever. And it floats around. It's not moored or connected. It doesn't have any propellers. And it'll sink down to about 3,000 feet or 1,000 meters. Then it sinks again further down to 2,000 meters and hangs out there. And then it jumps up with a buoyancy engine up to the surface, measuring temperature and salinity and nutrients and oxygen and pH and all these essential ocean variables. And it's this way that we know how the larger oceans are changing. When I got my PhD, I learned that the ocean was too big to change on human timescales. And that's wrong. What has happened in just the last 2 years has just completely revolutionized our understanding of just how responsive the ocean is. The ocean has taken up more than 90% of the excess heat from all the carbon we put in the atmosphere, all the thing we're worried about with global warming. Well, all that heat is mostly going into the ocean. Were it not for the ocean, we would not be here. So the oceans, this is a picture of the global average ocean temperature change, not just at the surface, but all the way down to a little over a mile, around 2,000 meters. Where it goes from blue, which is colder than average, to red, warmer than average. You can see in this particular case, the transition happens around 2015. But the real point that I want you to take home is this is not a surface warming problem. This warming is in some cases all the way down to the seafloor. It's not super warm at the seafloor. It's tenths of a degree warmer, but that's a huge amount relative to the normal variation that you see in the deep ocean. So the whole ocean is changing. And I thought I'd come here and talk to you as Coloradans and talk about things from Colorado that matter to you. And I realize that most of you are from elsewhere, but the point remains the same. If I talk to a Palm Beach crowd, I can talk about sea level rise, I can talk about sargassum, I can talk about really anything that matters to you snaps back to the ocean. In this case, this is actually a study put together by the University of Colorado. And this just shows the climate variable, which is heat waves, or cold waves, or droughts, or wildfires. And basically, all of these things are moving in directions that you know. In fact, I was just reminded about the ongoing drought that you're hopefully getting out of. All of these things, the confidence in the change from a neutral group of scientists and observers around the planet, these are all things that we have high confidence in that are actually happening. And these are things that can be demonstrably linked back to how the ocean is changing. So it may not feel like you've got a connection to the ocean here, but you do. So I'd like to posit that we use this kind of discovery where we advance the state of the art of how we see, how we infer, how we learn, how we use that knowledge to solve problems that matter to people. That embracing of ocean intelligence allows us to become stronger and safer and smarter. It just provides us with a set of intentional tools to face the future. But I'd be remiss if I didn't talk about something that is quite personal to me that we're going through right now. For those of you who have seen the President's budget for science, not just ocean science, but science altogether, this is my age of disruption at the moment. The NASA budget and the President's budget was reduced by about 53%. The National Science Foundation budget that funds all of science across the nation was reduced by 56%. The National Institutes of Health is 37%. It's going through this markup process. Fortunately, at the state level, there's some pushback on this particular budget. Honestly, I don't know where it's going to end. What I do know is that a cut in staff at this magnitude would pretty much stop everything that I've just talked to you about. I'd have to lay off half of my staff. We are developing plans to do just that. We may not have to do it, but that's what I've been doing over the last 4 months. It's very personal to me, but it's just to meet these men and women who are doing what they're doing. They're just amazing, dedicated people who are paid a pittance to dedicate their lives and knowledge. And it's just a beautiful thing, and it's a sad thing. But as Einstein once said, the measure of intelligence is the ability to change. And believe me, we are changing. We are being adaptive. When I was a research scientist at Columbia, the work that I was doing was actually studying how climate influenced human evolution. The short story is that everything that makes us human, our body plan, our upright posture, our hands, the size of our brains, our tool building, our language, our culture, that we live all over the world, every single one of those steps was a result of a shift in the environment where humans once lived. It either pushed them out, or made groups extinct, or selected for characteristics that we now define as being the single remnant of archaic human species. This was a book that we had written on this. This is us taking sediment cores. The takeaway point of my research, but really it's not about me at all, it's about us, is that the winning card for being human was being adaptable, being flexible, being able to change. Either being able to change because of a genetic advantage or a technological advantage or a body plan advantage. It ended up with us. And those junctures were sort of punctuated by changes in the environment. So we responded successfully as being the fortunate people on the other side of this by being flexible. And I'll just give you one example of this. This is the peopling of the world, the last out of Africa migration about 200,000 years ago. The entire peopling of the world with Homo sapiens, this whole storyline of populating all the continents of the world, was due to the transition from the Ice Age to the current warm period between 20 and 10,000 years ago. So I'll wrap it up by saying, our story as humans, our story as people that we're talking to each other, is one of adaptability, of flexibility, of innovation. And who are we going to do in this time is we're going to adapt. And we are. We're going to be flexible. We're going to meet the challenge. I'll leave you with this wonderful quote by Marcel Proust, which is, the only true voyage would be not to visit strange lands, but to possess other eyes. In short, we will evolve, we'll change, but as the young fish said to the old fish, from asking, what the hell is water? We instead turn to becoming explorers, innovators, and intentional protectors of the ocean that sustains us, and really an opportunity for us to really dive deeper into what it means to live on an ocean planet. Thank you.
Thank you. That was an amazing presentation. I could listen for hours more. I guess I'll have to come to Massachusetts. But
Yes, please.
I heard yesterday a really troubling report that ocean drones are going to be let loose in 2026. And I'm curious if they came and consulted you, they being, the Department of Defense, at any point about what this would do to our ocean environment.
Yeah, I've got the mic. Yeah, so I believe what they're speaking about in terms of ocean drones are not ocean drones the way you think of drones you see in the air or around here where there's just thousands upon thousands of these things. What I'm aware of that the Navy is doing is actually the opposite of that, which is developed very smart, very expensive singular robots that can go out and do a mission without exposing crew to hazard or to enter spaces where you'd be denied. And so the drone development that I'm familiar with, and we have a sector of WHOI that actually works with the Navy on drone development, is much more of this flavor of multi-million-dollar, single, incredibly capable vehicles that can be, I can tell you this, it was previously classified, but it's not now because it's been written up. We developed a robot that can swim on its own out of a torpedo tube of a Virginia-class submarine. It can run a mission for a duration of time and capability that I can't talk about. It can go out and do its thing, and then this is the cool part that was once secret, is that it can now navigate back into a torpedo tube that's only about 8 inches greater in diameter than the torpedo, than the vehicle. And it uses that with a combination of acoustics and lasers. And it's just an incredible tactical advantage that we believe is singular in the world. But that's the drone business that I'm familiar with, is not the sort of larger, not anything resembling that what we see happening, in light shows around the world.
From our online audience, how does the ocean neutralize the carbon?
Ooh, that's a great question. So the simple answer is, for those of you who ever had an acid stomach, you take an antacid. It's the same idea. Basically, you take, the ocean is slightly positive in pH, meaning it's a little alkaline. It has a pH of 8.1 or so, relative to neutral, which is 7. That's why the ocean is such a big reservoir for carbon. So the way that the ocean neutralizes that carbon is the ocean naturally can change its alkalinity, which is the opposite of its acidity. It does that through rivers and the like. In fact, I mean, there's a longer answer to that, but that actually proves to be one of the actual scalable climate interventions that could potentially actually reverse climate change.
Thank you. This was all fascinating. 2 things. Number one, I'm very concerned about microplastics and also about the huge amount of trash that they always highlight in the Pacific. And is there anything we can do about either one of those 2 issues?
Yeah, thank you very much for asking that question. And indeed, we actually have one of the larger groups in the nation working on plastics in the ocean in 2 ways. One is quantifying what is there, both how much and what kinds of plastic are in the ocean, how old they are, where they came from, where they're sourced from, those kind of questions, because you want to know how long the stuff has been there. But the other thing that we're working on that's actually really exciting is we've designed a center for ocean plastics, marine plastics, that would actually look at ways of developing plastic substitutes from marine polymers. That one of the great things about marine polymers is that they break down under ultraviolet radiation. One of the great things we learned from the Deepwater Horizon oil spill was that the leading cause for breakdown of the oil that was in the surface waters was actually exposure to the sun. And so one of the ways that microplastics, or one of the ways that plastics can disintegrate and dissipate much more readily, is using different kinds of polymers that actually disintegrate at the molecular level. So we actually have, we've developed a straw that costs, I don't know, 4 times more than a regular straw, but the straw does just that. So we've actually demonstrated that you can do this. So the answer is twofold. One is stop putting this stuff there. That's largely a Southeast Asia and Equatorial Africa source problem. There are interventions that are scalable there. Cleaning up the ocean is long and slow, and it's not foolhardy. It's long and slow and expensive. But the most promising thing in my book is that plastics are not going to go away, but changing the recipe for plastics so that they break down under ultraviolet radiation or they're more soluble in the ocean is the solution. And that's one of the things we're betting on.
What are the potential impacts of deep sea mining?
So do you remember when we went down in the sub, when we got into the Twilight Zone, what did you see? Lots of bioluminescent organisms. Remember, that's their language, how they find a mate, how they signal threat, how they basically do everything in their little deep sea lives is communicated through light. One of the consequences of deep sea mining is that the plumes that occur by siphoning up all that material from the bottom gets released right into the Twilight Zone. And so basically you're making the world's largest ecosystem a place where it's very hard for them to use their voice, to use their communication. That is the base of that whole ecosystem, which is I didn't mention this, but the fishery, if you will, of the mesopelagic, of the Twilight Zone, is 100 times greater than the surface ocean. So everything we get from the surface ocean, imagine there's 100-fold of that in the Twilight Zone. So it risks the very functioning, that other breath of oxygen you take, that's because of the Twilight Zone. So that's one of the impacts. The other is that, remember that little lowly sponge. That little lowly sponge is growing on those manganese nodules. This is where we find them. This is how we know these are the most fragile, precious ecosystems on the planet that we know painfully little about. And the little that we've gotten from it, again, from this little piece of paper, has been, these 3 anti-cancer drugs that have saved millions of lives. And we're throwing away that resource, that potential for discovery, for want of something that's actually not itself economically viable. And frankly, not needed, in my opinion.
So what is one place in the ocean that we need to explore right now that is poorly known or completely unknown?
Boy, what a great question. I think if you took away from this talk anything, it would be that the ocean is this interconnected network of life and fluid and flowing that sustains the entire planet. So the question is a little like, well, what part of a sequoia forest should would be the most interesting? What I would say is that just a month ago, a team of Chinese scientists discovered a whole new other way of a modality of life in the deep sea that was discovered by accident. And this was because they are investing like never before in ocean exploration for lots of reasons other than just intellectual curiosity. But that commitment to know and to learn, to pursue ocean intelligence, is reaping benefits to anyone who does it. So I guess my answer would be invest in the ocean.
Thank you for being here. Do we share ocean intelligence with other countries? Is there a race for ocean intelligence, like there was a race to space?
That's a really great question. And the answer is largely no. We share our data openly, internationally, freely with the world. those data that come up from Argo are made publicly available within, I think, a day after they go through a QA/QC protocol. That information, actually, I wrote an op-ed on this in the Washington Post about a month ago. That data is also used by our submarine fleet to inform where they can and cannot hide submarines, and both where they can find them elsewhere in the world as well. The commercialization of the ocean is proceeding at quite a pace, and actually now being led by the United States and China as they're trying to seek a strategic advantage. I would say that there's a lot that one can do in the ocean to increase ocean observing, to inform some of the questions we've talked about here. And those things can also be measuring something else that people can pay for. And so this notion that you just send one robot to measure one thing, we're now actually conceiving of, well, how do you build something that can actually have a lot of different sensors on it that different clients could pay for, in addition to the benefit of open science to humanity. And that's a place actually where I think there's some future for us.
What is science telling us about the effects of wind farms to the ocean?
Yeah, so we actually have a pretty large group of people who study wind farms. So one of the great things about the Woods Hole Oceanographic is that we're independent, and by being independent means that we're apolitical and we're neutral on issues of wind farms or anything else. We're like just the facts man, like in Dragnet, if you remember that. That's kind of the ethos at the Oceanographic. And so on the issue of wind farms, we do a lot of just the facts kind of science. So one of the studies we've looked into is what are the impacts of wind farms on marine ecosystems. One of the things we've discovered is that it does not appear to be impacting whale populations, other than it's a transient sound, especially when they're installing the wind farms. A lot of the marine life that we source for food, like lobsters and scallops and the like, we've discovered that they get acclimatized to the pile driving that goes in. Some of them actually look painfully like they're just like every time it goes, and they don't become acclimatized to it. And I sort of pity those guys. I don't know but we are actually looking into what those impacts are. There are other impacts too at large scale deployment that actually changes the ocean's ability to circulate and its ability to dissipate heat and the like. So there are some impacts. But that has to be weighed against the impacts of the power plant that wasn't built or the nuclear facility that wasn't built. And so what I would invite a bipartisan crowd is that the ocean itself is a bipartisan issue. Both sides there all love the ocean. It's one of the great things about studying the ocean is it just has that bipartisan support. And in terms of your energy future, I would just ask us all to say, everything's on the table. What do we want as a society? And that's a good conversation to have.
Peter, I'm going to ask the next question, but I'm going to plug 2 2026 programs as I do it. The first is around the energy question. We have a program on global energy coming in February. So that's on the blog, that's on the website in the announcement. And the second is space has come up several times. Came up in the last question. You referenced it several times. We have a program on July 6th that we're working with NASA and NASA partners on. We'll be out at Four Eagle Ranch in the patriotic spirit, celebrating American exploration in space. So the question is, I wonder if you can speak to the relationship between the oceans and space, and maybe WHOI and NASA. Illuminate those connections for us, if you would.
Yeah, happy to. One little factoid that probably many of you aren't familiar with is that there's a very intimate, long-lasting relationship between space and oceanography in the form of all of our ships are named after spacecraft, and spacecraft are named after ships. And so if you think of the spacecraft like Atlantis and things, it's actually after our Atlantis, and one of our ships is called the Armstrong. And so we have this sort of naming convention that's pretty interesting. And we have actually a couple of corporation members who are astronauts. So there's that kind of a connection, but that's not what you were seeking, I think. What's interesting to me is that, space really captures and inspires everyone. Every time we see something outside, like the new news of possible life on Mars. I don't know if you heard last week, they discovered new biomolecules, the strongest evidence ever that there was life on Mars. That just can't help but just capture our imagination. And I would say the exact same is true for our own ocean. And I would say that the frontier of knowledge is our own planet. What's interesting is that we spend 60 times more to explore space than we do on our ocean. So for every dollar that might go to oceanography, there's $60 going to space exploration. And as someone who lives here on Earth, and seeing what's happening to the ocean, if we could move from this to something a little bit larger, I guarantee it would pay dividends to all of society.
Hi, thank you. It was a great program. I have a question that refers back to one of your beginning slides. You showed the ships that go from New Jersey to Bermuda and back, and in this slide, the waters by New Jersey had all these different colors and things, and then as you got closer, it got bluer and bluer and bluer till you hit Bermuda. What did all that color represent in New Jersey? being from New York, I'm interested.
Yep. So in that case, it was just, so remember this robot not only detects 2 different kinds of algae, but it can do hundreds. And so imagine there could be hundreds of potential colors. I could just show you 2 because that's all we can handle as humans, just 2 variables at a time. So in that case, the yellow, the kind of warm colors were abundances of this thing called a dinoflagellate. The dinoflagellates are typically associated with coastal waters, and that's exactly what your eye picked up on. What your eye may not have picked up on is actually the boundary separating those warm colors from the blue changes seasonally and in part because of the seasons and also because the ocean is changing. So those are just 2 of dozens upon dozens of other things that we can look at. The idea is basically to develop this way to do an automated kind of ecosystem ocean health assessment for large ocean basin scale parts of the ocean. And what that tells you, for instance, in the dinoflagellates, so they're a harmful algal bloom. If you've heard of red tides before, they're a dinoflagellate. So if you're concerned about red tides, fisheries, these things encroaching on your aquaculture farm, you want our data. In fact, that's one of the biggest purchases of our robot is the aquaculture industry globally, because it's basically it's a autonomous sentinel saying no HABs, no harmful algal bloom is the thing HAB. It's like no HABs, no HABs. Oh, alarm, alarm, there are HABs coming to your salmon farm. And I don't know if you heard, but Australia had its biggest HAB outbreak in its existence. Our scientist, who is the leader in that, was down there, called in by the government to tell them, A, what was happening, because they had no idea, and B, what to do about it. We actually have developed an intervention that actually works. And because the funding has been cut, he can't do it in this country. I've got stories like that galore. I hate to say it, but there's, yeah, please.
What is the current and future safety of submersibles to be able to explore the ocean?
Yeah, so I didn't mention this with Alvin, but Alvin basically gets completely rebuilt every 5 years. It's a 40-ton, $50 million vehicle, only one like it in the world. So to get into this game of human-occupied submersibles is an expensive and, as some of you have read in the news, very dangerous endeavor. In our case, so I can say something probably in this crowd that I wouldn't say in my own, which is space is easy and the deep ocean is really hard. That is developing things that don't implode and you have the safety protocols needed to make sure that no mishaps happen, that is an incredibly arduous process that we actually have developed the protocols for that. And the checks that went into me being able to take that dive that I showed you involved months of work by a whole team of people whose job is only safety is job number one. Safety to the point where the culture of the group itself has very strict senses of personal behavior. In other words, they don't want anyone who takes risks. They don't want anyone who drinks. They don't want anyone who does stupid things. They don't want people who speed. You have to be in the job for your life, because the smallest thing can go wrong. Just give you an idea, 4,000 meters, the pressure on the top of the lid, remember I told you there's a hatch that's 19 inches? I calculated before I came down here. It's the equivalent of a fully loaded 747 sitting on the hatch. Not just that hatch, but then every hatch equivalent area would be having a 747 pushing down on it. The pressures and the opportunity for anything to happen. The implosion of the unfortunate submersible, the Titan, that likely imploded within a fraction of a second before any thought could materialize. It's not, when things happen, when things fail there catastrophically, they happen. You can't image it. It happens so rapidly.
So, Peter, we're close to time. And we've had a chance to learn from you, and now you've had a chance to learn from our audience. Get a sense of what we're thinking about, what we're worried about, what we're curious about, how much time we've spent around the oceans. I wonder if you can give us some closing thoughts. You were here 2 years ago. Maybe hopefully we can get you back 2 years from now for another update. But what can you send us back into the world with, thinking about?
Wow. I guess first and foremost would be something that really struck me as a 19-year-old when I discovered that I was going to be an oceanographer and not a studio art and math major. Alan knows the story. And that is the joy and the privilege and the wonder that comes from studying the ocean is second to none. It's one thing, hike beautiful trails and see incredible animals as you do here, but when you allow your mind to grasp the beauty of this planet, in particular the ocean, and we are predominantly an ocean planet, it's almost a spiritual kind of awareness that is kind of hard to put into words, but that kind of grace and that kind of gratitude for just being able to appreciate just how special this planet is and how we have to protect it is a journey I invite you all to take, either by visiting us or just learning more about the ocean. It just gets more and more interesting with every chapter. And I've made a career out of this, and I tell my students and postdocs and anyone I can that it's the best job in the world. It's just incredibly gratifying. And I'm grateful to be in my role to represent the men and women who do this, but it can go away. And so knowledge is fragile. And that's one of the things that's made me double down on my journey, is that I know that what we're doing and trying to do is one of the most important things I can do with my life. Thank you.
Ladies and gentlemen, Dr. Peter Menocal.
Thank you, James. Thank you.